Okay, today we're going to start section 3 of the chapter on dealing with the ideal gas equation. So we're going to take all the gas laws that we learned about and mash them all together and come up with a glorious equation for it all. And of course, they start out with some cutesy little thing to get your interest because they have to pander, I guess. What we want to do is we want to calculate pressure, volume, temperature, and amount of gas, moles in other words, using just one equation. Now, we haven't talked about moles yet in this chapter, and I'm sure some of you were happy about that, like Dawn, for example. So how does that relate to the gas law stuff? Well, there's a gas law that the book hasn't talked about, and it's really not one that's used as much as the others, but it's called Avogadro's law. Yeah, he did gas stuff too. The guy was into everything. So Avogadro's law says the volume of a gas is directly proportional to the number of particles, number of moles, really. Or to put it mathematically, V equals K times N, number of moles. But of course, we're not going to use that gas law, so you don't have to memorize that or use that equation for anything. Although you could use it just like any of the other gas laws. For some reason, the people who wrote your textbook didn't like Avogadro's law, I guess. But you'll notice it fits in with the other gas laws. I'm going to leave the power plant behind and do this on my own because it's what I do. Oops, there's some physics there. Don't worry about that. No, I don't want to save it. So far you'll notice we had PV over T equals constant, right? And that gave us all the different gas laws. If you hold temperature constant, PV equals K. And that was Boyle's law. If you hold pressure constant, you get V over T equals K, and that was Charles' law. If you hold V constant, P over T equals K, and that's Guy-Luszak's law. Not the way Sebastian spelled it, by the way. And now we find that moles relate here too. Notice moles relate directly to volume, just like temperature did. When you increase temperature, you increase volume. Well, if you increase moles, you increase volume. An easier way of saying that is if I add more gas, the balloon's going to expand. So it turns out that number of moles is going to go down here with temperature because it varies in the same way as temperature varies with volume. So we can put that down here and get PV over NT equals K. In fact, in the last section where we did PV over T for sample 1 equals PV over 2 for conditions 2, we could have thrown N in there, made it PV over NT equals PV over NT, and solved for all kinds of fun stuff. We didn't do that. But the important thing is that PV over NT equals a constant. Okay? Now, before, if we just did, say, Boyle's law by holding both these in the bottom constant, remember with Boyle's law, we held the amount of gas and the temperature constant. That random K for Boyle's law included the N and the T and the actual constant. Same for all the other gas laws. If we had V over T equals K, that's because pressure and number of moles were held constant and they were incorporated into that K value. But once we have this PV over NT, we've taken everything about the gas out of the constant. So this constant that's left truly is a constant. It's, for our universe, it's the same value no matter what. And so rather than call it generic K anymore, we give it its own symbol, and that symbol is R. I don't know why. I guess a pirate invented it and liked to call it R. So we can really rewrite this as P over V, PV over NT equals R now, the actual constant that we choose to call it instead of just generic K. But of course, we could rewrite that using some simple algebra. Take this denominator, multiply through to bring it up top, and you get PV equals nRT. And that is the ideal gas equation. It combines all the gas laws together. Boyle, Charles, Guy-Luszak, all of them, even Avogadro's law. all combined into one glorious gas law. And once we know the value of R, and again, it's a universal constant, which means anywhere you go in our universe is the same value. Once we know the value of that constant, we can plug in 3 of these values and find the last one. So if I know the temperature, the number of moles, and the volume, I can calculate the pressure. With the other gas laws, we didn't have that luxury. We had to know one set of conditions first, P1, V1, and then solve for V2 or whatever. Here you don't need that anymore because we have a universal constant that works everywhere. So as long as you know R and you know 3 of these 4 variables, you can find the last one. The value of R itself, of course, depends on what unit system you're using. If you're using atmospheres versus kilopascals versus whatever, milliliters versus liters, whatever, you have to use kelvins, you have to use moles. The unit system that your book uses is kilopascals for pressure, liters for volume, moles, and kelvins. In that unit system, R equals 8.31. Why? Because that's what it is in our universe. There's no reason for it. It's just that's the value it is with that unit system. If you use different units, like atmosphere for pressure, for example, you'll get a different value of R, 0.0821, which you're not going to have to know. When you take AP Chem next year, I'm looking at you, Angelina, you're going to have to use a variety of different forms of R, but not this year. Let's come back to the PowerPoint and finish this up. So they just got done telling you about Avogadro's law without telling you he did it. So moles proportional to volume. Putting it all together, we get PV over NT is constant, which I just showed you. And so you can write it like we did with our old gas laws, P1, V1, and all that, equals P2, V2, and all that. That's just in a giant version of the combined gas law. But even better, you can do this and set it equal to the constant, which we know is R. And if you plug in known values, for example, we know that at STP, 1 mole is 22.4 liters. So you plug all those values in, and you find that R equals what I told you, 8.31. Well, they're going to take a while getting to that. There it is, 8.31. Notice liter kilopascals per mole Kelvin. Again, if you use a different unit system, like for example, atmospheres here, it's going to change what R is. But for us, we're going to always stick with liters, kilopascals, kelvins, and moles. What if I give you milliliters? Well, luckily, you know how to convert milliliters into liters. What if I give you atmospheres? Well, you'd have to convert atmospheres into kilopascals. I do that to my honors class. I'm not going to do that to you guys because I like you better. So there's the equation, PV equals nRT. It's the point of today's lesson. So now let's do a sample problem, and then I'm going to give you a worksheet where you can do, I think I gave you 5 different problems for that, and make sure you got it. So, well, let's see. Here we go. She doesn't look very sassy today. They give you a temperature, 34 Celsius, nitrogen gas, who cares? It's an ideal gas. So all gases behave the same way as long as they're ideal. We'll talk more about that tomorrow. So they give us the temperature, 34 Celsius. They give us the volume of the tennis ball holding the gas is 0.148 liters. And they give you the pressure inside there, 212 kilopascals. Notice that's higher than normal air pressure. That's why the ball stays inflated. If it was less than air pressure, the ball would kind of collapse. Now, so they give you the temperature, they give you the volume, they give you the pressure. You know R. So they ask how many moles of gas are in there. Well, we can easily now plug in. We're given 1, 2, 3 of the 4 things. We're asked to find the 4th thing, the moles, and we know R. So there's what we know. The 3 variables they gave us, don't forget, temperature's got to be in Kelvin. Everything else they gave us in the right units, which was rather nice of them. And there's R, because we know that. So there they convert the temperature. Now we know PV equals nRT. I don't know why they feel they have to put the little X's for multiplication in there. You're not in 3rd grade. You don't need that. but PV equals nRT. We can simply plug in pressure, volume, R, and T and solve for moles. What, of course, the textbook does is they rearrange it on you first. Well, you can plug in first and then rearrange. Your choice, doesn't really matter. But we can now find the moles by plugging in pressure, volume, R, and temperature. And we do that, and we get 0.00123 moles. They put it in scientific notation again, just to be obnoxious. Does it make sense? Well, it's a small tennis ball, not under ridiculously high pressure or temperature, so yeah, the moles are going to be, there's not going to be much gas in there. By the way, let me just go back for a moment. You now know the number of moles of gas in there, don't you? Oops. Knowing that, you could do anything with that. You could calculate, since you know it's nitrogen, you can calculate how many grams of gas you have, because you know how to convert moles into grams. If you knew the grams, you could calculate the molar mass of the gas, because you know molar mass is just grams per mole. So once you have moles, you can get anywhere. You might have heard me say that 1 or 2 times before. But one of the values of this ideal gas equation is it lets us get moles. In fact, it was one of the early things that Avogadro worked on that allowed him to calculate numbers of moles and figure out, well, he didn't figure out, but ultimately how to figure out what Avogadro's number was. So that's that. One more example. Here they give you a volume of gas. Now it's 10 to the 6th liters, so they give you a big volume of gas. Who cares that it's methane? Just don't light a match. They give you the pressure of the gas, very high pressure, and they give you a temperature. Yeah, they're ugly numbers. They give you the temperature in Kelvin, which is kind of nice. Ugly numbers, but they'll work. So they give you the volume, the pressure, and the temperature. You want to find the kilograms of gas. Well, first find the moles. And then convert to grams. So PV equals nRT, rearrange, solve for moles again. And you get a lot of moles here because it's a whole cavern filled with compressed gas. But now that you have the moles, we know it's methane. We get its molar mass, and they gave it to us. I think it was 16. We can do a moles to gram conversion. You're not allowed to forget those older chapters. And now we have the grams of gas in there. And of course, from grams to kilograms, you slide the decimal, and we get 2.05 times 10 to the 4th kilograms, which is a lot of methane. But it's a whole cavern full of methane, so I guess that's understandable. Okay, who cares about that? And that brings us to the end of today. Tomorrow we're going to get into real gases and how they differ from what we're predicting with our equations. All these gas laws, Boyle-Charles, up to this one we just did, are all assuming that gases are ideal. In the real world, of course, things don't always act in an ideal manner, so that's tomorrow's lesson. For today, I'm going to give you a worksheet. You can do a few problems on the gas law we just did, and then turn that in to me. And have a good rest of the day.